Hello everyone, welcome to this course of Advanced Mechanics of Solids. In this course, we'll be mostly talking about beams and plates. Will not be restricted to just the simple deformation of beams and plates. Rather, we'll also be interested in the kinds of deformations which are induced through elastic instabilities. And the way that we're going to proceed to address these various kinds of deformations is through a very mathematical way, a very general mathematical way, which is referred to as the calculus of variations, and which, as you can see on the screen, is the first chapter that we are going to address. Now, I want to think of this chapter much in the same way that we had addressed the first chapter in our previous course of applied elasticity, which was mathematical preliminaries. So this first chapter of calculus of variations here is like the mathematical preliminaries of advanced mechanics of solids. However, comparing with that earlier course where you had some notion of tensors, vectors, and things like that uh, in applied elasticity, here I'm sure some of you have not even heard of this phrase, calculus of variations. So uh, it's a doubly dangerous kind of situation. So neither do you know the definition of this phrase, and here I am asking you to be motivated to study this. So what's the way out? So what I'll do is I'll first briefly tell you the motivation of this calculus of variations, thinking about it just like a method which is very useful. So you think of it as some method called calculus of variations. It could be any other name. And then what is the motivation for this? In terms of things which you are already very familiar with, governing equations, boundary conditions. And then once we have that motivation in hand, we'll try to understand what this calculus of variations is about. Now, as we had done previously in applied elasticity, when we were talking about the mathematical preliminaries, we did not take a too formal approach. In a similar fashion here also, we are not going to take too formal an approach. In fact, it is going to be utterly and completely informal, mathematically speaking. Rather, we are going to take up a very utilitarian kind of approach, meaning that whatever we need, that only we will try to learn. Okay, so this is certainly not a maths course. It's very much a course in mechanical engineering. We wish to proceed accordingly. Okay, so first of all, what is the motivation for studying this calculus of variations? Why this particular method? What benefit does it afford us? So uh, I could write this down, but I think it will be just faster if I quickly tell you the points, which is that first of all, if you just accept the fact that calculus of variations is some method, some mathematical method, then this provides us with some sort of an algorithmic approach towards getting or obtaining the governing differential equations of various mechanical systems. Various mechanical systems relevant to the context of advanced mechanics of solids could be beams and plates, which we'll study throughout the semester. But more importantly, once you learn calculus of variations, you'll have to appreciate the fact that this is not just limited to things like mechanics of solids. In fact, calculus of variations has wide-ranging applications in various branches of physics, not just mechanics. So once you learn it, the general unified principles on which this is based can very well be extended to study various kinds of topics in physics, starting from electrostatics, optics, and so on and so forth. Okay, so it's a really worthwhile pursuit. Next, through this use of calculus of variations, you will see that not only the governing equations come out in a systematic fashion, but together with the governing equations, almost magically and automatically, the boundary conditions also emerge. Okay, so in certain situations, it may be quite difficult to arrive or to guess, as we have been doing till now, the boundary conditions. But through this method of calculus of variations, we'll be able to follow a very systematic, unified way of arriving at the boundary conditions. In fact, for certain instances, you will realize once we do them that if you had not proceeded by the method of calculus of variations, there is no way you could have arrived at the correct set of boundary conditions. It is that useful. Okay, and finally, slightly more philosophical point is that the calculus of variations, it has a very natural connection with things like finite element methods, which some of you have already learned in the previous semester. Uh, so, so if you study advanced mechanics of solids, things about beams and plates using calculus of variations, then it provides us a natural link towards proceeding to numerical solutions of problems. Okay, so this is the background motivation. Now, with this motivation in place, I think it's no longer wise to delay talking about what this method is all about. And as I said, we are not going to take a very formal mathematical approach. Rather, it's a very utilitarian kind of approach. So we learn what we need to learn. All right. So uh, let me just switch off this video here, uh, and then let's get down to the business end of things. So to understand the calculus of variations, we are not going to directly launch into what this definition is and so on and so forth. Rather, we'll start with something which is very, very familiar to us from differential calculus. Okay, so free your mind completely and just think of a very simple kind of situation, that we have this kind of uh, we have, suppose, a function like this: y is equal to 3x squared. So this is something that I have arbitrarily picked up. It could be something else. Okay, where this x is lying between certain in a certain domain. Okay, so this closed domain x1 x2, this x is lying between that. Okay, so all of you know how to find out, if I ask you find out the minimum value of this y within this domain, all of you can find this out. Okay, you differentiate this once with respect to x, set it equal to 0, find out the extremum points, then find out the second derivative, uh, uh, set that to be find for what value that is greater than 0 for the extremum points, and then you can say that, okay, for those points for which the second derivative is greater than 0, you get the minimum. All right, so far so good for differential calculus. Next, uh, consider this integration. Okay, so I am presenting things to you almost disparately, but you will soon realize what's the connection. Okay, so consider this integration. I is equal to some integration of some f of x with respect to x within the limits x1 and x2. Now, when we learned integral calculus, our primary concern was to find out, to learn ways to find out this integration. When we could not find it, we went for numerical methods, maybe through some numerical techniques that you learned in your undergraduate days. But that was the whole idea, that given a certain integrand, given certain limits, you find out the value of this integration. Okay, all of you are familiar with that. Okay, now I want to change the nature of the question that we want to ask with regards to this integral, with regards to this integration. So what I want to say is that, okay, if we are given a certain f of x, we know various methods of finding this integration. We can find out this value I. But suppose I tell you that you are kind of free to choose this f of x. Okay, you are free to choose this f of x. Of course, there will be certain constraints. You can't take anything or everything that you want. There will be certain restrictions on the choice of this f of x. And like, had we been presenting in a very mathematical way, we would have said that you are restricted to choose this curve f of x from a set of admissible curves, where the admissibility would be defined through certain conditions. Okay, so if you are more mathematically inclined, probably that last sentence I spoke would make more sense to you. Anyway, so what we are really interested in getting at here is that if we take different values or different choices of this f of x, certainly this integration value is going to change. So for example, if we substitute this 3x squared itself here, okay, this is going to give us a certain value of I. If we take a sine x or a cos x or some complicated expression, that is going to give us certainly different values of I. Now, question is, from among those admissible curves f of x, like among those choices that we're allowed to make, uh, what is that choice which is going to give us a minimum value of this I? So you see what I have done here. Earlier, this was a simple curve, and we were interested in finding out the minimum value of y at a certain point x. But now we are changing the question with regards to this integration. What we are saying is that what is the choice of f of x? Okay, we are talking about the choice of the curve now, not about any specific point, and we are asking what choice of that f of x it is we are going to get a minimum value of I. So this is a very interesting question. Now, interesting is one thing. Question is, where exactly do we need this, and what at all is the connection with advanced mechanics of solids? So we are going to proceed towards that step by step. So first of all, forget about advanced mechanics of solids for the time being. For just try to see a couple of examples where such a question, okay, such a interesting kind of question has some utility. So first of all, you see, uh, let's take this example that try to find a curve. Okay, try to find a curve. Okay, find a curve between 2 points such that the length of the curve is minimum. Okay, now if you just think about it for a couple of seconds, you'll realize that what you're basically asking is that if basically a proof of the fact that if you join 2 points by a straight line, it is going to give you the minimum value. But how do we arrive at that mathematically? Okay, so that is one. That's the simplest possible question you could ask in the context of this kind of questions. Okay. Next, so how do we really express this? So suppose you have a curve, a general curve, uh, y is equal to f of x, and we want to represent the length of that curve between 2 points. So that length will be given by this expression. So let me write it down, and you'll be able to figure out what exactly is going on here. Okay, so you think of it like this, that suppose this is our x and this is our y, and we have this uh, one, this is our x1, and let's say this is somewhere, this is x2. So of course you know that the curve which is going to give us the minimum distance joining these 2 points is going to be a straight line. But suppose you did not know this and you took different choices of this curve like this. Okay, so what we are saying here is that if you take a little infinitesimal segment over this, the length of that is given by this square root of dx square plus dy square. So think of it like this. So this is that part. We are zooming in here. So this is that part. So this is the dx and this is our dy. So this length approximated by a straight segment, that is square root of dx square plus dy square, and if we integrate between the limits we get the total length from here to here. Okay, so our objective here is to minimize this capital L. Okay, and we can rewrite this expression in a certain fashion. So we can write it like this. Okay, or this dy dx, from now on we'll just write it like y dash. So this L is equal to integration x1 to x2 square root of 1 plus y dash square integrated with respect to dx. So that thing we have to minimize. Okay, right now we are not going to launch into the actual procedure of minimizing it, but we have just formulated the problem. Another example, uh, so in this new page, let me just discuss that, another example. So uh, now consider a, a frictionless uh, kind of path between 2 points, and imagine that you have a, a, a little particle moving down that path. Okay, so let me just pictorially depict it. Suppose you have a path like this. Okay, some arbitrary shape, and this is frictionless, and uh, some so we have maybe uh, we are considering this kind of a ball which is just moving down this path. You some people try to or present this problem like this is like a wire, a frictionless wire, and there is a bead here, a little bead which is moving down this wire. I mean, you can think of it in various ways. uh, doesn't matter because this is frictionless. So the question is, what is the shape of this path between these 2 points, such that when this bead or this particle is moving down this path, it is under the action of gravity, mind you. Then what is the shape of this path which will minimize the time of travel? Okay, so let me restate that question again. Find the shape of this path, of this frictionless path, such that a particle moving down this path under the action of gravity, uh, it, it covers this entire path in the minimum time. Okay, now this is a very famous problem in the entire history of calculus of variations and mechanics in general. Uh, uh, so had we been doing a an entire course on calculus of variations, we could have gone into the history of all that. It is the famous brachistochrone problem, and there are various YouTube's videos on this. Uh, you can try to take a look on that. Uh, so the problem is like this, that uh, find the shape of the frictionless path such that the particle traveling down it under the action of gravity. Sorry about that. Under the action of gravity, uh, takes the minimum time to cover the path. So all this is fine. How do we express it in terms of an integration. So note that we are interested in finding out the minimum time. So let us set up our integration in the form of a time. So think of it like this, that we have a distance and we have a certain speed. So we have already seen how we write the distance. We're going to utilize that, and then the speed. Okay, but this speed of course will be dependent at which position of the path we are in, and of course cover this entire path. So note that this v will be equal to square root of twice gy. Okay, so if you're not sure how this came about, what you can do is you can just do a conservation of energy, like kinetic energy is equal to potential energy. From that you can find this out. You have learned all of this in high school physics, so I'm not going to go into the details of it. All right. So if we replace this here, you'll see that this can again be written like y dash square uh, as gy. This entire thing is under square root, and this thing here is a dx. Okay, so t is equal to this entire thing. We have to find out, we have to find the minimum t. Okay, and again we are not going to go into the exact method which we use to find out this minimum t. Rather, as I said, this setup we are going to use as motivation for studying the calculus of variations. Okay. Okay. Now, if you look at this previous example here, okay, where we are talking about the length of the curve between 2 points, this L is dependent directly on the first derivative of the curve under consideration. Okay. Next, so if you think of it like a general integration, this integration is dependent on what? It is some function of the y dash. Next, you see here, what are the things involved in this I? So if you think of this t like a general integration, it is dependent on y as well as y dash. So previously it was just y dash. Now it is both y and y dash. Okay, so this gives us a motivation of thinking about a very general I. Okay, so when we talk about these kinds of minimization problems, uh, what could happen is that this general integrations, whether it is length, time, or any other thing which we are trying to minimize, that could depend, as we have already seen, on y dash. It could also depend directly on x. We have not seen an example involving that, but it could be there. And there could be higher order derivatives involved also. Okay, there could be even higher order derivatives involved. So this is a very general way. Now we have been talking about minimization. Now there is nothing so sacrosanct about minimization. It could very well be maximization. Okay, so maybe maximize a certain area or maximize a certain volume. That could also be a question. So what we are really interested in here is extremization. Okay, could be minimization, could be maximization, but we are more generally we are interested in extremization of this I. And because we are interested into in going as we go forward, in taking some concrete steps to demonstrate what is going on and what should be done, instead of taking this very general kind of dependence on various higher order derivatives, uh, it will be useful if we just restrict ourselves to x, y, and y dash. The principles remain the same. You can extend the theory to higher order derivatives, but to see clearly, as I have told you earlier, we are going to take a utilitarian kind of approach. What we are going to do is we'll restrict ourselves, restrict to this kind of a situation. Okay, with the understanding, with the implicit understanding that the theory that we develop and the understanding that we gain from that can very well be extended to integrations involving higher order derivatives also. All right. Now, and again, I emphasize that we are not restricted to minimization problems. It could very well be maximization problems also. So, in general, extremization of I. Okay. Now, whenever we think of this kind of extremization, because we are so very familiar with our notions of differential calculus, and we are saying that time and again we are saying that the way that we go about searching for this minimum value or the maximum value of I is by changing or by taking different choices of y. Because note this, y is the curve of concern here. Okay, so back when we did this, back when we were talking about this first very familiar example, y is equal to 3x square, and I asked you that you find out the minimum value of this y, of course you are going to do dy dx. Okay, so much in the same way, our initial temptation when we are talking about the minimization or the maximization, more generally the extremization of I, with respect to different choices of y, the temptation, the initial temptation, okay, the temptation is to do something like this, di dy, okay, but this is wrong, can't do that. Okay, so why can't we do that? Well, there's a very subtle reason here. You take this first example that we were considering. Okay, so we had this x here and we had this y here, and we were considering various curves between these 2 points with the objective of finally arriving at that curve. We know the answer, of course, that it's a straight line, but we are our plan is that we are going to arrive at it, at the answer systematically, that what is that curve which is joining these 2 points and such that the distance is minimum. So when we do that, we take different choices of this curve, like this, like this, we don't know. Okay, we take different choices of this. So when we do that, what are we doing? Basically what we are doing is we are sitting at a certain x, and here we are taking different values of y. Okay, we are sitting at a certain x and we are taking different values of y. Again, we are sitting at a certain x and we are taking different values of y. Okay, so think of it like this. I think students find it useful to think of it geometrically like this. However, when you talk about dy, it has a different notion. Okay, so dy, as we have already seen, dy is like this. Okay, so when you think of dy between, so this is our dy, that dy is associated always and always with a certain change in dx. So dy is always accompanied by dx. Okay, you cannot have the y changing when you are writing in terms of this notation dy. When you are writing dy, you have to understand that that dy always has as its partner a change in x also. But this thing that we are trying to do here, in order to arrive at the correct curve which will give us our answer for the minimum value of I, for that we are not changing x. X is constant and we are changing y. So this change in y is represented by a different kind of differential. So this is like the variational kind of derivative. Okay, this delta y. Okay, so this delta y is for a fixed x. This is the primary difference. This delta y is for a fixed x. This dy is always accompanied by dx, which is why I always emphasize to my students that you must be very, very careful in not using this kind of a notation, because some students do have a habit of using this because of some bad habits acquired in high school, of writing partial derivatives sometimes using this. This delta has a very specific meaning associated with a fixed x. Okay, so you should not be arbitrarily using it. You should only use it only when you mean this kind of a variation. Okay, so so we have basically through this discussion we have learned what not to do. Question is what to do. Okay, that answer we have not even not yet given. So if we can't do this kind of a di dy, question is what we should do actually. So right now we don't have any answer. Okay, and when we don't have any answer in a fundamental problem like this, we have to go down to the basics. Okay, so what is the basics? Basics is what we were discussing back in our first slide, in our first page. Okay, at the very top is y is equal to 3x squared. All of you know how to minimize this, but given that we are now at a critical juncture of exploring a different kind of minimization or a different kind of maximization, or in general a new kind of extremization problem, let us go down to the basics of how to, or how we arrived at the method of finding out this extremization here, and perhaps from those lessons we'll be able to export the idea to the current uh, objective. Okay, so we are going to go down to the development of the method which gives us the algorithm for finding out this minimization or maximization, and then our hope is that we will be able to export the same kind of idea, the fundamental idea, not directly the method but the fundamental idea, in the case of this kind of a extremization of integrations. Okay, and that we are going to do in our next video lecture. So with this I end this part of the lecture. Thank you very much.